What is a vacuum? For most people, what comes to mind is a region of space with no air at all. But if you have even a basic understanding of quantum mechanics, you will know that even when there appears to be nothing in space, quantum fluctuations still exist. As the saying goes, a vacuum is not truly empty. So does an absolute vacuum exist in a theoretical sense? And how far has modern science progressed in its understanding of the vacuum? In this episode, we divide the vacuum into 7 levels and analyze them one by one, to see just how deep your understanding of the vacuum really goes. Level 1. Vacuum, no particles. In everyday life, there are actually many situations involving vacuums, such as vacuum packaging or vacuum-insulated bottles. In industry, any environment below 1 standard atmosphere can be called a vacuum. Depending on pressure, these are further classified into low vacuum, high vacuum, ultra-high vacuum, and so on. For example, the Magdeburg hemispheres experiment you learned about in school, those metal hemispheres that even teams of horses couldn't pull apart, contained a high vacuum environment inside. In most people's imagination, if we remove every last bit of air from a container, that should be a true vacuum. But this kind of vacuum only means no air. It does not mean the space is truly empty. We often equate outer space beyond Earth's atmosphere with a vacuum, but in reality, space is still filled with cosmic rays and various forms of radiation and particles. At the very least, the fact that you can see light means that photons must be present. Even if you could block all external radiation, including the cosmic microwave background, the container itself would still emit radiation. After all, anything above absolute zero theoretically produces thermal radiation. So, if there were a perfectly sealed environment, with not a single particle inside, and no radiation emitted by the container itself, then it could indeed be considered an absolute vacuum in the electromagnetic sense. But such a vacuum clearly does not exist in reality. Level 2. Vacuum is not empty virtual particles. Although an electromagnetic vacuum does not exist in reality, let's assume that such a vacuum did exist. Would it truly contain nothing at all? Of course not. Even if there are no real particles, virtual particles would still be present. What exactly are virtual particles? No matter how much you know about quantum mechanics, you've certainly heard of the Heisenberg uncertainty principle. It is one of the most fundamental and foundational principles of quantum mechanics. Simply put, it states that for certain pairs of physical quantities, such as position and momentum, or time and energy, we cannot know both values precisely at the same time. Take position and momentum as an example. When we precisely measure a particle's position, its momentum cannot be measured accurately, and vice versa. Note that this lack of precision is not due to technological limitations, nor because of some external interference. It is theoretically impossible. That is why the principle was renamed from the uncertainty of measurement principle to the uncertainty principle. The same applies to time and energy. We cannot determine both simultaneously. If we constrain time to an extremely short interval, then energy becomes highly uncertain. This phenomenon applies even to the vacuum. Over extremely short periods of time, the energy of the vacuum may not be zero. Energy can spontaneously appear, manifesting as the random creation of particle-antiparticle pairs in the vacuum. These spontaneously created particles are called virtual particles. Why are they called virtual? Because they exist only on paper. That is, during calculations. Assuming the presence of such particles makes the process much simpler. And crucially, these particles quickly annihilate each other and disappear, returning the borrowed energy back to the vacuum. It is as if nothing ever happened. This is what we call quantum vacuum fluctuations. From this, we can see that energy conservation is not an absolute rule. It holds more accurately in a global, averaged sense. So, on a macroscopic level, a vacuum appears to be a space with no particles. But on a microscopic level, the vacuum is filled with virtual particles generated by quantum fluctuations. That is why we say, the vacuum is not empty. Level 3. Vacuum is not empty quantum fields. You might ask, aren't virtual particles just hypothetical constructs used in calculations? Can they really be considered real? That's correct. Virtual particles are intuitive concepts introduced for convenience. They are not real particles in the traditional sense. However, in terms of physical meaning, the interactions they represent are very real. Because the effects that virtual particles have on real particles can be directly measured, we can say that virtual particles do exist, just not in a form we normally imagine. As quantum mechanics progressed, physicists eventually unified quantum mechanics, special relativity, and classical field theory into a comprehensive framework known as quantum field theory. In quantum field theory, both real particles and virtual particles can be regarded as ripples in underlying fields. The difference is that real particles can persist and propagate, making them directly detectable, while virtual particles are extremely short-lived. They appear briefly and vanish almost immediately. We can only infer their existence through indirect effects. So from the perspective of quantum fields, whether particles are real or virtual, the vacuum is always accompanied by one thing: quantum fields. Level 4. Vacuum is not empty. A relative vacuum. Just as there is no absolute time in relativity, vacuum may also not be absolute. As quantum field theory matured, physicists began exploring how to incorporate general relativity. While studying quantum fields in curved spacetime, they theoretically discovered a strange possible phenomenon. If you accelerate through a vacuum at absolute zero, you would find that the vacuum appears to have a temperature. However, this temperature exists only from your perspective. To an external observer, the same region of space remains a zero-temperature vacuum. This reference frame-dependent temperature phenomenon is known as the Unruh effect. In general relativity, acceleration and gravity are equivalent. This means that near extremely strong gravitational fields, such as those around black holes, the Unruh effect may cause the system to emit thermal radiation. In other words, black holes can have temperature. If black holes have temperature, they must radiate energy outward. So where does that energy come from? That's right, from virtual particles. This is the true origin of Hawking radiation. So whether a vacuum is empty or not, whether it contains only virtual particles or real particles, can depend entirely on the choice of reference frame. Why don't we usually consider reference frames when discussing vacuums? Because although there is no absolute reference frame in theory, there is one that is particularly special. When dealing with large-scale cosmic evolution, the cosmic microwave background radiation, people often ask, relative to what is the age of the universe measured? You can think of it as being measured relative to the cosmic microwave background. It represents the universe's own clock, also known as cosmic time, because Earth's gravitational field is weak, and relativistic time dilation is minimal. We can treat Earth and the cosmic microwave background as effectively sharing the same reference frame. The same applies to vacuums. Under normal conditions, the Unruh effect has an extremely small influence on the vacuum, often far beyond our ability to detect. Level 5. True and false vacuums. False vacuum decay. As we just discussed, the vacuum contains various quantum fields. For most quantum fields, there exists a lowest energy state, called the ground state. A field in its ground state is at minimum energy and maximally stable. However, there is one field in our universe that is not currently in its most stable ground state: the Higgs field, which gives fundamental particles their mass. Although the Higgs field has remained in its current state for 13.8 billion years, the fact that it is not in the true ground state means that this stability is only temporary. It could, at any moment, fall into a lower energy state. This means that the vacuum throughout the universe today may actually be a false vacuum. If, at some point, the Higgs field's potential were to suddenly drop to a lower state somewhere, the false vacuum would become a true vacuum. This transition would then spread outward in all directions, at nearly the speed of light. This phenomenon is known as false vacuum decay. False vacuum decay is somewhat similar to the two-dimensional foil effect. Space collapsing into a lower dimensional state at light speed, without stopping. But unlike that scenario, false vacuum decay would cause many fundamental particles to lose their mass. All structures in the universe would disintegrate, and the laws of physics would be completely rewritten. In short, when the Higgs field falls into a lower ground state, space would become a truly true vacuum. Level 6. Different vacuums. Vacuums in string theory. Although quantum field theory can handle most situations today, when confronting extreme problems, we are forced to rely on a future ultimate theory. As one of the leading candidates for such a theory, string theory has long been controversial, yet mathematically, it offers an entirely new perspective on understanding the vacuum and even the universe itself. During early research into superstring theory, physicists discovered that our universe should have 10 dimensions, but according to relativity, even counting time, we only have 4 dimensions. So where did the other 6 go? Just as string theorists were at a loss, the Kaluza-Klein manifolds proposed by mathematician Xingtung Yao provided a breakthrough. Soon after, a paper titled The Vacuum Structure of Superstrings was published. String theorists proposed that Kaluza-Klein spaces formed by these manifolds have dimensions unlike ordinary three-dimensional space. Their dimensions have finite size and cannot extend infinitely. the extra 6 dimensions we cannot observe, are believed to be compactified into tiny Calabi-Yau spaces at the Planck scale. At first, everything seemed perfect. But, inevitably, problems emerged. There is not just one kind of Calabi-Yau manifold. Current estimates suggest that their number, if not infinite, is astronomically large. Each distinct Calabi-Yau manifold corresponds to a unique space, with its own physical laws. Which one our universe belongs to, no one knows. This strange implication of string theory seems to suggest from another angle that a multiverse may truly exist. Thus, across different universes, physical laws may differ, including the very concept of what a vacuum is. Level 7. The end of the vacuum nothingness. Even before introducing Calabi-Yau manifolds, string theorists had already discovered that some extra dimensions could only exist at microscopic scales. Because of quantum uncertainty at such scales, these extra dimensions may not be stable. In a 1982 paper discussing the instability of Kaluza-Klein spaces, Edward Witten, later known as the father of M-theory, proposed a decay mechanism even more terrifying than false vacuum decay. Witten found that in vacuums described by Kaluza-Klein theory, if extra dimensions shrink beyond a certain threshold, the vacuum can collapse into a single point. At that moment, dimensions cease to exist. This is the end of the vacuum. Unlike the gravitational singularity of a black hole, which exists within four-dimensional spacetime, this decay initially forms a point that rapidly expands outward at the speed of light. Even more bizarrely, although it expands, because it has already lost its dimensions, from our perspective, no matter how large it grows, it remains a point. This is the terrifying nature of Kaluza-Klein vacuum decay. Compared to a black hole's singularity, it does not merely end spacetime, it allows that end to spread outward. And compared to false vacuum decay, this process does not change the state of the vacuum, it annihilates the vacuum entirely. If the space created by the Big Bang is merely the familiar, narrow sense of space, then the end of space means that even the most general form of space would cease to exist. Could this be what we call nothingness?